Several years ago, I was approached by Hydreco Corporation of Kalamazoo, Michigan, in regard to a hydraulic valve that they had manufactured. It was a prototype valve, and it had failed during laboratory testing, short of the 2 million fatigue life cycles that they had wanted. They also were interested in raising the operating pressure of the whole hydraulic system from the level at that time to something higher, perhaps as high as 5,000 psi. So I'd like to discuss some of the concepts of the hydraulic valve as a small structural system modeled by solid elements, and at the end I'll make some conclusions about how you can scale the results for a family of bodies that are geometrically similar. Jim Glidden was a vice president for engineering at that time, and he had once attended the University of Michigan, so he was a little partial to coming back to his alma mater and seeing if there would be someone there that could analyze his valve. Lanny Becker came along also. This company is about a 2-hour drive from Ann Arbor, where the University of Michigan is. The company manufactures hydraulic equipment and does a lot of work for the makers of off-road equipment such as Caterpillar and John Deere and the car companies in addition. The hydraulic valve in question was a 3-bore valve. I've done a rough schematic sketch here to show that there were 3 holes bored through the basic block here, which is actually a casting, and in each of the holes you have 2 plungers. Now these plungers act as control valves, and they open and close certain passageways to the high pressure hydraulic oil. This casting itself is basically rectangular in shape, but is very intricately carved out in the interior. When it's molded, it's actually a sand casting and has quite an intricate core. I didn't realize how they made pieces such as this, but the core was basically a sand core with some aluminum stiffeners and then glued with an epoxy type glue to form a rather substantial body that was put in the interior. Then the external cavity was made in sand, and then the item was cast. After cooling, it was reheated, and the core was melted out, so to speak. The epoxy glue was vaporized, and then all the sand and aluminum stiffeners in the core could be literally poured out through the holes that had been cast into it for the ultimate bores. Let me describe the problem in this figure. That the valve housing is a single piece casting made of gray iron, the 3 bores that we have mentioned. It's used on heavy equipment. It might be mounted, for instance, on the dashboard of a road grader, where you would see the operator furiously moving levers back and forth, and you see there would be a total of 6 such levers. It would lower the blade perhaps, and perhaps turn the wheels and so on. The casting was cracking during the fatigue test at the parting line of the mold, which is the center line in a horizontal sense in our in the way that I showed the valve. There was some offset present in the prototype casting, so there was a little joggle right at the minimum section, and this probably precipitated the fatigue problem. The internal pressure they were using in their test of this device was 3,000 psi, and they operated the casting through many cycles of pressurization, hoping to reach 2 million. My understanding was it cracked somewhere around 1 million cycles, so they were failing to reach their goal. So my challenge was to analyze this housing and then to propose a redesign. And in that goal, I'd have to consider stresses and displacements. Of course, the fatigue or any other material failure like that is often a problem of a stress-induced failure. On the other hand, the clearances of the plungers in the bore and some other sliding problems might be governed more by the displacements of the body. I was asked to make some estimates of the expense of doing a finite element analysis and then the time elapsed. Although the original problem in full would be a large project, I decided it would be possible to solve by using reflective planes of symmetry a 24th of the problem, basically. There's a horizontal reflective plane, a vertical reflective plane longitudinally, and then the different bores can be separated by reflective planes. There's some approximation in that. But when you do that, it appeared that I could analyze that small portion of the body with 1 month's effort at about $5,000 in time and materials. And then I thought that additional cases could be done for about a week with $1,000 expense. Now, the reason this was attractive to these people was because they were spending 6 months and $10,000 to get one prototype made. And if they had to repeat that process with an actual physical casting, they required another 6 months and another $10,000. So it wasn't really a very good way to do rapid turnaround on a parameter study for design, whereas finite elements is pretty well suited for that. Additional cases are quickly done once you have a database. Well, let's talk about the physical modeling involved. It's clear that this valve housing is a solid body. It's not plates or beams. The material should be acting in the linear elastic range because the internal pressure should not be sufficient enough to yield a material or distort it very much through large deflections. In fact, since fatigue is the ultimate failure criterion, usually fatigue would occur at a modest stress compared with yield stress. So we expect small displacements. We don't expect large angular changes and large strains. The loading is entirely a pressure loading due to the hydraulic oil itself. It turns out there are 5 reflective planes of symmetry, and I'll sketch those in the next figure. There's a lot of symmetry in this problem. That's what helps us isolate the one section. An interesting thing is that 2 of those 5 reflective planes of symmetry are moving planes, and they must be allowed to breathe because of the internal pressurization of the casting. Let's look at the 3 reflective planes of symmetry that are to be fixed. I've cross-hatched those in red here, and they've been arranged in such a way that they cluster around the axis of the bore here so that that will remain fixed, and then the body will move in relation to that. In the bottom figure, that would be at the point here. That's useful because you can look at what was once a circular hole and see the elliptical shape after deformation. Now, I modeled this problem, particularly this part that I'm going to circle here, and loaded it and found to my surprise that the body compressed instead of expanding. And after thinking about that, I realized, yeah, that's true because I have the load on the one bore over here, the load on the other bore over here, and that tends to put this section through here in compression, and it does compress. But you know that's not right when you inflate a body with some enormous pressure and the thing starts to shrink on you. So after a lot of worry, I realized, say, what I'm not doing is resolving the live forces on the mirror image body that we've removed to the left and is not modeled. It has these live loads on its bore, and those aren't being reacted. So rather than having a free edge on the left, which I had been doing, I realized that I had to have a moving plane of symmetry which had acting on it the resultant force of the live loads over here in order to complete this repetitive pattern. I have seen that situation referred to as generalized plane strain. It might happen in the case, let's say, of a propane tank to be filled with high-pressure gas. And if the tank were dominantly a cylinder with spherical caps at the end, and you analyze just a segment of the cylindrical portion and made those cuts, you would realize that you'd never develop any axial thrust from a free body diagram that didn't resolve the gas pressures that were on the gaseous phase of the body. But yet that has to be reacted sooner or later against a far wall. And that's what happens in our case. And by the way, it also happens at the far wall of the bore as viewed from this side view. And this area that I'm cross-hatching here also has pressure acting on it, tending to pull the far moving reflective plane in that direction, in the y direction. So that would be on the far side, and it also must have to have a live load acting on it. I was also asked to consider several other design changes. One might be that we would switch material from the gray cast iron with a modulus of 18 million psi over to a malleable iron with a modulus of 24 million psi. And that's a rather easy thing to do in a finite element study. Also, I was to consider possible changes in length scale by a factor of 2, either scaling up or scaling down. That's a little tougher, but you can just modify the grid locations by a factor of 2, and I did that later with small Fortran programs. Let's consider the finite element modeling for this project. I solved the problem both with SAP6 and then at a later time with MSc Nastran. I'll explain the Nastran solution first and then back up and say some things about SAP6. The elements that I chose were the 8 to 20 noded hexa elements, and it only required 88 of those. So this is a rather small problem by industrial standards. I used the P-load forward cards for the pressure entry. Then I used the permanent single embedded constraints on the grid cards for the 3 reflective planes of symmetry. And in each case you constrain the surface so that it cannot move normal to its plane. For the moving reflective planes, that's a little trickier. Nastran has an RBE2 card, which is a rigid body element, which can tie together the nodes along a surface such as this, and then have a master node that controls the motion of all the degrees of freedom perpendicular to the plane. Then we had to apply the unresolved forces that were on the mirror image bodies that weren't modeled, and I applied those with force cards on the RBE2 element, applying the force directly on the master node. Now when I did the SAP6 solution, which was earlier, they have a feature called tie nodes that plays the role of the rigid body element, such as the RBE2 element. I also found that between those two software packages that Nastran is a little fussier about element distortion. And of these 88 elements, I had to subdivide about 6 of them before I could get it to run in Nastran. So apparently the error checking and the quality of mesh is tighter on Nastran than it was on SAP6 at the time I did this problem. Let me sketch the model that we've developed from a different angle. And now with the origin of coordinates here, we see one of the moving reflective planes cross-hatched in green, whereas we also see the red cross-hatched planes that are fixed. There would be another moving reflective plane on the far side in that direction. There would be another fixed reflective plane on the far side in that direction. The high-pressure fluid can move through this channel. It can move in this channel here. The plungers use this surface as a mating surface. So it was hoped that that surface would not go out of round very much, because if it did, then you could get blow-by of the hydraulic fluid. Now, The company was not able to get earlier measurements than these analytical predictions because it's very hard to put strain gauges in here in an instrument. It's such a corrosive and high temperature environment that it tends to strip the strain gauges right off. So the measurements were lacking, and our theoretical predictions were going to be the first firm figures that they had on what was going on inside their hydraulic valve after making them for something like 40 or 50 years. I resolved to model the body with entirely hexa elements and without any pentas. That was a little bit noble, and I think probably not worth the effort because it took me a whole week to figure out a hexahedral pattern to fill that shape. Here's the final result. I found that I could do it with a modest number of elements, 88, to predict the high stress region. But the connectivity was really strange on this. Because of the fluid opening on one face that exited on another face, it was very hard to complete that pattern with all hexahedras. And I think that shows why even today it's difficult to fill any volume with hexahedrons. Many people are giving up on it, and I have decided to only fill with tetrahedrons for these automatic meshing schemes. Now, I did this by hand. I carved up a large block of polyurethane foam. Jim Glidden always used to laugh that I had carved up our family sofa to do this, but I really didn't. And I painted with water-based pens the outlines of the various elements, and then I had to wash it off and redo that once or twice before I got the final pattern. The final mesh for MSC Nastran had 88 hexa elements, 1,300 degrees of freedom, which is a rather small problem by today's standards, and 547 nodes. In the computer usage at the time, it took quite a while to do the decomposition even after resequencing. Today this would take much, much less time, and I imagine it would be a matter of 5 minutes on a Hewlett-Packard workstation. The CPU cost likewise has dropped tremendously from the $175 previously. Such a run commercially would probably be less than $50 now. So labor is higher today, but computer time is cheaper. At least let's say computer calculations per calculation are substantially cheaper. I was surprised by one practical aspect of this problem, and that was that I thought that oblique views of the mesh would be most useful to debug. And yet I found that the traditional orthogonal views in engineering drawing were really the most valuable. The reason is that the pictures are much cleaner when you do that. Oblique views give you such a forest of points that when one of them's wrong, it's difficult to tell. But the top and the end views shown here were relatively easy to debug. Now, there were some sharp angles in here you can see in some of these regions. It gave me some trouble, and Nastran asked me to subdivide those elements essentially. It said there was too much distortion, and the thing that can commonly happen is that the Jacobian goes negative somewhere. So you can't distort the elements too much, or the mapping onto the double unit cube cannot be done. Let's look at the numerical results first after our computer run. For the 3000 psi pressurization case, the measure of precision came out to 10 to the minus 13th, this value of epsilon. That would be the force on balance compared with the forces at a node, and so our solution still had some 13 significant figures. Strain energy was rather small, in English units about an inch-pound. And that's an interesting thing, and it shows that in spite of the relatively high pressures in hydraulic systems, that if you have rather rigid bodies, then there's not a lot of energy stored. On the other hand, in the hoses and the more flexible parts of the system, then you can get substantial energy, and that becomes a problem when there becomes a leak. I've heard of systems jumping up in the air and hitting the ceiling, in fact. Well, that energy wouldn't have come from the energy stored in this this solid material casting because it just does not store energy. The holes did become elliptical as we'd expected, but the magnitude was larger than was hoped. It was 0.005 of an inch on the radius, and that turns out to be 0.13 millimeters on the radius, which is really quite a bit. This was probably almost an order of magnitude more than the company had expected because they were honing those surfaces to be mirror-like. Now they do need that anyway to be to have the proper wear resistance, and so that's an important feature and a useful one. And it turns out, if this is the way the valves have been running over the years, then it turns out that the system's more forgiving than people thought, and you don't get that much blow-by, even when there's some modest gap opening up. One reason you could imagine this is that the fluid has to travel some distance through a small gap like this, and there'd be a lot of viscosity preventing it from doing that. And then the internal stress at the point of failure turned out to be 22,000 psi, or 152 megapascals, and this also was larger than the company had expected. Now, their design goals were to have something more like 12,000 psi, so this was outside their hoped-for range. On the other hand, it was a prototype casting, and the production castings were a lot cleaner. And so the little joggle, or the offset, in the upper and lower halves of the mold may have actually had more to do with the failure than this stress, which still is not extreme, but important anyway in fatigue. In looking at displacements, it's now that it pays off to have had two of the reflective planes fixed in space. You see at the upper right corner then, what I've done basically is fix a point in space here. And then the bore that here was circular to start with, along this contour here, has become elliptical. It's actually pulled in a little at the diameter shown here, and then becomes elliptical moving outward with a major diameter here. And that's the one that has the 0.005 inch deflection. Now you'd have a mirror image situation on the left side over here. Well, have to be careful speaking about mirror image. Can I say that? Yes, I can, because the same body is repeated over and over, at least for this vertical component of deflection here. That would have to be the same. The body does not have reflective symmetry about this plane. We've already called on as many reflective planes as we can. Notice that the base of the hydraulic valve tends to move downward further below the bores, which are relatively weak points. And so you can see that pressure is expanding the body in kind of a reasonable way, because here on this major vertical direction it's much stronger, and you don't get as much deflection down here. I've just sketched the maximum stresses on the critical parting line where the fatigue occurred. There were two nearby minimum sections that essentially were like stalagmites and stalactites connecting the top and the bottom half of the casting. And interestingly, on both of those, we got a high stress on the order of 22,000 psi on the left there and the right over here. The stress fell off then in the other corners of these same bodies, and yet the cracks that resulted did penetrate through this whole distance. So once the crack started, it was able to run into the lower stress regions, and it did propagate through the minimum section, which makes sense. There was a second region of modest stress, and it was at the bottom of one of the hydraulic fluid channels. The highest stress such point was this one, and from neighboring elements I predicted stresses of 15, 18, 5, and 5,000 psi. Now, Unfortunately, I didn't have a fine enough mesh in that area to really resolve that, although you can see the average would be something on the order of 10 or 11,000 psi. So if that area were important, we would have had to remesh and come up with a finer mesh there. Lanny Becker did say that he'd seen cracking in a different kind of valve in that general region at the bottom of the fluid passageway, but not in the current one that we were studying, which was just a prototype, by the way. And by the way, I should mention in defense of everyone involved that this was an experimental valve that wasn't put in production, and in fact the company has not had failures in the field of this kind at all. So I think that they're a very conservative company that likes to have things last forever in the field, and both their fatigue and their stress goals are very, very conservative goals. I wasn't able to do one of the things I had hoped, and that was to put out some kind of a little brochure on improved valve housing design or some such thing. I thought maybe there would be some rules of thumb that would be evident that could help a designer. Well, we could say a few things, but we really couldn't codify the results very much. We did certainly analyze the existing baseline design and found the points of highest stress, and they did coincide exactly with the fatigue cracks. We did realize that those stresses were higher than expected by the corporate engineers, and they had hoped for stresses more in the 12,000 psi range, which is pretty conservative. Also, the displacements were higher than had been expected. Now, a mitigating factor there is that we put the highest pressure on this system, and we didn't include any stiffness due to the plunger being in the bore. Now, presumably on the portion of the bore that wanted to close down, if there was a rather rigid body there, it couldn't close as it did. That was on the minor diameter of the ellipse. Now, one design concept that I believe is appropriate, though, is that these column-like regions, and I've called them stalagmites and stalactites because you see they hang down from above and stick up from below. The current design, by necessity, had a circular bore here, so they really had to have a circular cutout there. But then the fluid flow was allowed to have a wider passageway on the right, but that left us with an area that was a little bit like a curved column or a curved beam column. And actually, it would be better if that were straightened out by perhaps removing material on the left, which really wasn't possible because of the need for the bore and the seal there. On the other hand, you could maybe make both sides circular like this. So I've called this the better design. The problem there being that that would then restrict the fluid flow in the fluid passageway on the right. So you really can get boxed in design situations. In addition to technical conclusions, there were some management conclusions. I did spend $6,200 in time and materials on the project in spite of my estimate of $5,000. Jim was really good about that. I brought it up during a dinner conversation. We were evaluating some workstations, and we were in Colorado at the time. And during the meal I'd said, Jim, you know, times are tough. Boy, I've got 2 kids in college, and a little while longer I complained about the cost of inflation and so on, and about dessert. I said, and you know, I spent $6,200 instead of $5,000 on the project. And he said, oh, that was okay, Bill. He knew it was a tough project. And so, boy, did I ever enjoy the dessert. At that time, that difference in pay meant quite a bit, it turns out. It also took me 5 weeks to do the project instead of the 4. It turns out I'd done it right through a summer conference, which really diverted me, needless to say. Now, I really feel the technology is excellent here, that the application of linear finite element theory to hydraulic valves and hydraulic pumps and so on is an excellent use of the theory because of the small deflections. On the other hand, it's hard to convert our analytical results to design rules of thumb. So we sort of had some hits and some misses. We ended up with a good database that I was able to use for further runs. In fact, I did some 14 additional runs on parameter studies, and that's one of the advantages of such a model of a system like this, because you can do parameter studies and you have the same errors baked into the baseline model as you do the perturbed model. So when you get a fractional change in performance, it's likely to be pretty accurate. Those additional runs cost as little as $450 when I did it for something as simple as changing material properties. For instance, if you change Young's modulus to the malleable iron, we found that stresses didn't change at all, but displacements were inversely proportional to that stiffness. Now, many people know from college days that if you have a problem that's entirely a stress-posed boundary value problem, then the stresses don't change when you change the material. You see, the load paths have to be unique, and so it's just a matter of channeling the forces through the system, and the materials don't matter. If you have a mixed boundary value problem, however, with displacements prescribed somewhere, then you get into the problem of displacements being affected also. But our problem was relatively simple. Another thing that happened was geometric scaling didn't affect the changes. I actually ran another case where I scaled this pump up by a factor of 2 in every length dimension through the placement of the grids, and the stresses didn't change at all. And that showed that the pressure acting internally was scaling in such a way in this problem when we kept the 3000 psi to not affect the stresses in the body. That's not obvious. I'm going to do some scaling arguments like that in a minute. Additional runs helped identify the value of adding material. I added material to the backside of one of those posts to help make it more straight, and indeed that helped by some 10% on the stress, but on the other hand blocked the fluid flow enough that that was viewed as not a serious candidate for change. Then I added an inch of cast iron to the bottom of the housing. There was no space problem with that, but there is a weight penalty, and that also improved the stress situation by about 10%, but would have added so much weight that it wasn't a cost-effective change. All told, there were some 14 runs, and I think we gained intuition and insight with each of those runs. The design was a complicated design, and I think it is a sort of situation where such analysis needs to be done for each new prototype as it comes along. I find the concept of scaling to be very interesting, and this is the concept that when a body is geometrically scaled up or down in size, what happens to the internal stresses and displacements in the body under a given set of loads. Now, we can take two subdivisions at least, and one is pressure loads, where the pressures are acting on surface areas, and so you can see that in a way the loading is going to change at the same time the size of the body is. Another class would be gravitationally loaded bodies, where you have the body's own weight acting as the load, and therefore as you raise the size of that body, you raise the loads. These are both somewhat self-imposed load systems. So let's look at the pressure loading first. Suppose you had two of these bodies, and of course I was thinking of the hydraulic valve when I sketched these, that here you have a two-bore whole body with pressure on the inside of the bores. Here you have a similar body that's twice as big in every dimension. Now that means in fact there's 8 times the volume, but we need to look at the scaling. If you have the same pressure loading here and here, how does that affect the stresses in the body? Well, since the force in the body is acting upon a surface area, that means the forces actually are going to scale as the length squared, and that will come in a minute. Stress for the direct stress case would be a P over A type of loading, and In this case, it would vary as the load above, which we've just said would go like length squared, and then the cross-sectional area on which it's acting varies as the length squared, and that ratio is just unity, so that the direct stress, in effect, does not depend on the length scale. It's just a constant. Bending stress might be different. We know that it's typically an MC over I formula shown here. The moment is a force times a distance, or a moment arm, and that is in turn a length squared times a length. Then the distance to the extreme fiber back here is a length, and the moment of inertia scales like length to the fourth. So all told, when you put these together, you get length to the fourth over length to the fourth, and again, that doesn't depend on the length, and you have a constant situation. Therefore, the larger body will have the same stresses as the smaller body. That's not obvious, but it's helpful because, at least for people making hydraulic equipment, this means if they geometrically scale their bodies and use the same pressure level, then the same stress levels will be found. A second kind of scaling would be that of bodies exposed to gravitational load. So these are self-loaded bodies. Now that actually happens more than you might think. For instance, in vehicles, we often talk about how many G's acceleration are put on an aircraft. And you see that means how many times its own weight is a maneuver causing in terms of load. So let's think of that then. Here you have an airplane of a certain size, and then you double that size. What happens to the direct stresses, for instance? Well, this time the loading is going to go like the length scale cubed, because this body is volumetrically loaded. And so it's in the case of direct stress, the P over A now becomes length cubed over length squared. And that means that your stresses go as length to the first power. So as the body gets bigger, then the stresses are higher. Likewise, bending stresses with the MC over I, you find that the moment is a force times a distance, but the force is again like L cubed as up above, and then the distance like a length. Then you have the distance to the extreme fiber C, which is a length scale here, and the moment of inertia, which is length to the fourth power. So all told, this also scales like length to the first power. And what it means is, whether direct stresses or bending stresses, that